All right, so we're ready to resume where we left off in class today. We have been introducing ourselves to the topics of kinetics, and in a little bit we'll come back to this. The more times we see it, the better. But the first thing we learned was that the rate of a reaction is in some way related to the change in the concentration of your chemical over time. If this is a reactant, it would have this negative sign. So I'm going to put that negative sign there because this is a reactant that we're usually going to be looking at. And then we also saw that the rate of a reaction is equal to K times the concentration of the reactant raised to an order. So this first one, remember, was our average rate. The second one was our instant rate. All right, telling us how fast the reaction is going at any moment when we know what the concentration is. Right? The other way to think about this equation is that we can use this to be predictive about how much chemical we need to accomplish a certain speed. If we desire a reaction to have a particular speed, this equation lets us figure out how much chemical we need to bring that about. Okay? So these are two different forms of the rate law. In a little bit, we're going to do something with these two that is going to be very important in terms of a third form of a rate law. But what I want to do right now is go through some examples of how we find the K and the N. Because again, we said that K and N, the order, are the defining traits of a reaction. Okay. Now, some ways to know the order. That's the big thing. One is if we are given K with its units. At the end of class earlier today, we were looking at how the different orders each have their own respective set of units. And so that is sort of a clue as to what the order of the reaction would be. If I said to you, a reaction has a rate constant of 0.5 reciprocal seconds. Those units, reciprocal seconds, only belong to a first order reaction. So I've essentially told you a first order reaction has a rate constant of 0.5. All right, and you see it's hidden in the language that is the units. Okay, so that's one way that we can find the order of a reaction. The second method that we'll get into right now is what's known as the method of initial rates. And this will look very familiar because the comparisons that we did during lecture this morning for the three different reactions, A to 2B, C to 2D, E to 2F, where we looked at the pattern that was at work. When we changed the concentration, what happened to the rate? That pattern we could use to figure out the rate of a reaction, now that we understand that it controls this exponent that we're looking for. Okay? And the third way, which we'll get to at much later in the class today, will be with what are called the integrated rate laws. Okay? So that'll come in a little while. So these are three different ways that you can essentially determine what the order of your reaction is. The rate constant is usually found by substitution then. So it's usually more important to find the N, and then you use it to find the K of a reaction. All right? So let's look at the method of initial rates first. Okay? We can determine the order of a reaction by comparing different trials of the reaction that have used different concentrations the change in the rate will be related to the order, as we saw earlier. Okay? Now you can do this two ways. If you're good at seeing patterns, like I tried to point out those patterns in lecture this morning, you can sort of mentally just figure this out. But if the numbers are challenging and you don't see a direct connection, like the numbers were pretty simple in the example in class this morning, there's going to be another way that you can do it sort of more mathematically. All right? So I'll walk you through that. But really the basic idea that you're going for, if you want to do it by inspection, as what's called by inspection, you look for a factor that relates to concentration values, and then you look for the factor that relates to rate values. And then what do? You relate the concentration factor to the rate factor. It'll come out being 0, 1, 2, etc. Okay? Now again, as I mentioned in class, any order is potentially possible, but we are going to make life simple in that only integer orders exist for our purposes. All right? Only integers exist, and positive integers, 0, 1, 2, and 3, and higher. Okay? So a method of initial rates problem would present you with a reaction and then a few sets of data. For example, 2 NO2s decomposing to 2 NO plus O2. What you could control in this reaction is the initial concentration of NO2. Right? So a little subscript of 0 means that you're dealing with time being 0, or the starting or initial concentration. All right? It's different from the little superscript of 0 that we've seen, meaning standard. Okay? So maybe I tried this reaction 2 times. And in the first trial, I used 0.015 molar, okay, nitrogen dioxide. And in the second trial, I used 0.005 molar. So that was my independent variable. And then what I observed, the dependent variable, is the rate of this reaction. So for the first trial, perhaps it was 1.22 times 10 to the minus 4 molar per second. And for the second trial, it was 1.35 times 10 to the minus 5 molar per second. Okay? This is all the data we need to find the entire rate law. That's our goal. So the rate law of this reaction would fit the generic pattern. All rate laws fit a pattern that rate equals a rate constant times the concentration of your chemical, in this case specifically NO2, raised to an order. So what we really need to do is find K and N. And we'll end this problem by rewriting this generic form with a number here for K and a number up there for N, such that you could plug in any number you want here and it would tell you what number you have here. Okay? All right. So now we can do this, like I said, by inspection, looking at patterns, or in a second we can do it sort of mathematically as well. All right? So if you remember the numbers that we had in class earlier for our different reactions, what we tried to do was relate, one of these trials to another. So actually going backwards in this case from trial 2 to trial 1, the factor here is 3, right? I've increased from trial 2 to trial 1. Doesn't matter which one we really did first, okay? But from this one to this one, this 0.015 is 3 times as much NO2 as this other trial. What is that factor is the question, right? So how did that change? And so here the numbers aren't quite as clean and as easy to see as they were in the last examples that I gave you in class. But if you took one of these divided by the other, you'd see that this is approximately, a factor of 9, right? And so how does 3 relate to 9? It's a square, right? So this would be like that third reaction we looked at earlier, E to 2F, because when we doubled it, we saw a quadrupling in the rate. When we tripled it, we saw a 9-fold increase in the rate of the reaction. We're matching that same pattern, therefore this is a second order reaction, okay? And so we've gotten the N, all right? Now we would get K by substitution, all right? Now that's how you do it by inspection. It's a little bit tricky, and boy, where's the work? If you've made any error, where's the partial credit that I can give you? It's pretty weak, right? So I kind of discourage you from doing it, all right? It's good in that you could get an idea of what the answer is, and then you could prove it the longhand way, all right? But if you did this, like I did right here, I would understand that, actually. That's your work, and I might be able to give you some partial credit for that, all right? But if you had times 3 times 9, and then you wrote n equals 3, you'd be wrong, right? I would say, okay, you made a mistake here, and then I would make some kind of deduction. Okay? All right, now let me show you the more mathematical proof of this. So the way to do this mathematically is to understanding that each and every trial of a reaction follows the rate law. So in other words, for trial 1, the rate, this 1.22 times 10 to the minus 4, equals the unknown rate constant times the concentration, 0.015, raised to the nth power. Okay? So all I did was substitute the numbers for the 2 different placeholders down here in the rate law. But how many unknown values are there in that equation? 2. There are 2 unknowns there. Okay? So if you remember some rules from algebra, you might remember that an equation or a system with 2 unknowns needs how many equations in those same unknowns to be solved? It's also 2. Okay? And it leads to a system of what are called simultaneous equations. So we can get our second equation by looking at our second trial. Trial 2, the rate of 1.35 times 10 to the minus 4, again equals K, this time times 0.05, raised to the same value of N. You don't want to change K, you don't want to change N. They are the same from one trial to the next. But now we've got 2 equations in the same 2 unknowns. Right? And what we got here?
Is it to the negative 5? Trial 2.
Oh, it is to the negative 5. Thank you. That would be important. Yeah. Okay. All right. So, anybody have an idea of how you might solve at this point? What's something you could do to solve for either K or N?
Divide by like the computation to the N to solve for K.
Okay. So, did you say solve for K in trial 1 maybe, and then substitute into trial 2? It's one idea, right? We could solve either equation for the K value symbolically and substitute it in down here into the second equation. The K would disappear, then we would only have N. Or vice versa, we could solve for n and substitute it. That's a classic way to do this. All right. Here, we can do something a little bit different, a little bit of a time saver. I can actually divide one trial's law by the other. Divide one equation by the other. All right. When I do that, I want to see exactly what the number is. I get on the left side 9.04 equals, okay, now k over k, this is now an algebraic expression, so the two k's reduce. Essentially, I've done what I said earlier. I have solved one equation for k and substituted it into the other. All right, so k is being eliminated. But what happens to this piece? We need to know a rule of exponents. I heard someone whisper subtract, and that's the wrong rule of exponents. There are two rules of exponents that we often confuse. So I've written a to the x over b to the x, and a to the x over a to the y. Which rule do I need in this application? I need the first one. I have the same exponent but different basis. Okay? Now, this second one is the ax minus y, but that's not what we're doing right now. This one, I can regroup a over b. I can combine them to the one case of the exponent. This is savvy because now instead of having two different ends, we're always trying to group our unknowns together. Now they're all together. And what is 0.015 divided by 0.005? It is 3 raised to the nth power. So I'm kind of doing what I had over here by the inspection, actually. Here's the times 9. Oh, there's the 9 almost, right? Here's the times 3 factor. Oh, there's the 3 factor. All right? So now, technically, to solve this problem, you would take the log of each side. Because when you take the log of an expression with an exponent, you bring down the exponent, okay? And so then n would equal log of 9.04 divided by the log of 3, and then you can figure that out pretty simply. But a separate way to do this is to read this sentence. To read the question that is before you, all right? And to remember that I'm really trying to make life easier for you. Remember that your answer has to be a whole number. Keep that in mind. You're targeting a whole number right now, or 0, 0, 1, 2. Now with that in mind, answer this question. 9.04 is 3 raised to what power? That's what this sentence or question says, isn't it? Or if you could read it from right to left, 3 raised to what power is 9.04? Does everyone know the answer to that without having to use a calculator, I hope? It's pretty much 2, right? When you think about it, could be 0, 1, 2, or 3. Okay, I just told you the rules of my game that you have to get a whole number. So yeah, this is like 2 point something, some infinitesimally small number, all right? But you have to get a whole number as your answer. So use some common sense, all right? And just read the question that's there for you. And you know that, second power. Therefore, n is 2. And we've got the same conclusion that we had over here. Okay? Now, how do we get k? Now we substitute for k. So it doesn't matter which trial we choose now. If I take trial 1, 1.22 times 10 to the minus 4 equals k times 0.015 squared. I'll just divide the 0.015 squared, and I'll get k equals 0.54. And it's going to be 1 over molar seconds. Because this is a second order reaction, I know those are the units. So now, final answer time. The rate law of this reaction, its rate will be 0.54, 1 over molar seconds, times the concentration of NO2 squared. Do you see how I'm not putting in one of the numbers for concentration? I'm putting in a placeholder that you can choose whatever concentration you want right now. And this will tell you how fast your reaction is. All right. So it's sort of a generic equation that lets you control the rate of the reaction. Or vice versa, if you want a particular speed for this reaction, you could solve for what concentration you would need to do. All right. Are there any questions? And think about the second class. Do you have any questions for them, on their behalf? No? Okay. All right. So they had no questions for you guys who are watching the video. Okay. All right. Now, let's do another one of these with 2 reactants and see how it might be a little bit different. All right. When we have 2 or even 3 reactants, we just have to do a little bit more work, because each reactant has its own order that we have to solve for. And the key to having multiple reactants is to designing the experiment so that only one variable is independent at a time. Okay, we can't have 2 things changing in terms of concentration, trying to figure out which one caused the effect that we see on our rate of our reaction. So I'll just use a generic reaction here, A plus B to give me C. In this case, I could potentially have the initial concentration of A and the initial concentration of B. And I could see how each of them affects the rate of the reaction. So these molarities, these will be molarities, of course. Okay. So in my first trial, I'm going to use 0.5 molar for both A and B. And my rate is going to be 8.5 times 10 to the minus 5. In my second trial, I'm going to change my A up to 1.0. So this is just like we saw earlier. You want to change A. But I cannot also allow B to change. So B has to be 0.5 here, so that whatever happens in my rate column, I can attribute to what happened with A. Right? If this changed, I wouldn't know how much of the change in rate came from A and how much of it came from B. All right? So what I'm really doing here is isolating A's impact on the rate of the reaction. Okay? So 34 times 10 to the minus 5. It's kind of weird to put it that way, but this lets us ignore the powers of 10 and just compare these numbers actually. It's a little easier. Okay. And then for trial 3, I'm going to return A to its original value, and now I will increase B to 1.0. Okay? And I get 8.5 times 10 to the negative 5 again. Okay? So now you could be doing some by inspection work right here. And I would encourage you, in this case, to get one of these orders by inspection. Does anybody see anything real quickly that jumps out to them? What the order of either A or B might be? Morgan?
B is 0 because it's not affecting the rate.
Okay, we've got someone saying B is 0 order because it doesn't affect the rate, and that's correct. When we look at the change in B, when A stayed the same, so we know A might be doing something, but what it does in both of these trials is exactly the same. So whatever happens over here was caused by B. But nothing happened here. And earlier in class we said that that means the order is 0. So the by inspection for 0 order is really easy to get. Question?
We know that the concentration affects the rate based on the order, but is there ever a situation where the order itself might change?
No. For a given, the question was, can the order change? No, it cannot. The order is set for a rate, for a law. The rate constant can change when temperature changes, something we'll look at later in the chapter. All right, but once you know the order, regardless of the temperature or other experimental conditions, that order is set in stone. And that's actually due to the collision theory that we'll look at the end of this chapter. Okay? Yeah, so that makes life easier. Okay? All right, now how would we find these values if we didn't do it by inspection? So our generic rate law for this reaction is that the rate is going to be equal to a rate constant, again K, times A, which needs raised to an order, and B, which needs raised to an order. So I'm going to use a different letter. I'll just use M to represent the order of B. So last problem I needed to find K and N. This problem I need to find K, N, and M. I need to find each one. Okay? All right, so comparing trials 1 and 2 will give me the effect of A, and comparing trials 1 and 3 will give me the effect of B. Now before I jump in and start doing what I did for the last example, I just want to ask you a real quick question, right? We had the 9 equals 3 to the M, or N, last time, right? Not hard. Now what about 0.111 equals 0.333 to the N? Which do you like solving more? This one on the left or this one on the right? On the left, pretty quick, right? The whole numbers, right, rather than the decimals. But they're the same. They have the same answer. This is 1 over 9 equals 1 over 3 to the N. The way that this would become this is by the order that we compare them. Okay? So the lesson that I'm getting at with these two things here is when you go to do this comparison, put the larger rate, put the rate that is larger in the numerator. That's all you got to do. If you put the smaller rate in the numerator, so if I just compare 1 to 2 right now, I'm going to get the decimals because 1 is smaller than 2 for the rate. So all I have to do is flip it and put 2 over 1 in this case. All right, so a little bit of lesson in thinking about our design. Okay, so I'm going to do trial 2 divided by trial 1 this time. Trial 2 is 34 times 10 to the minus 5 equals K times 1 to the N and 0.5 to the M divided by 8.5 times 10 to the minus 5 equals K, 0.5 to the N, 0.5 to the M. So what drops out? The K's drop out, but also 0.5 to the M. I don't know what M is, but 0.5 raised to it is always going to be the same thing. 34 divided by 8.5 is 4. 1 divided by 0.5 is 2. Again, here we've got an easy question staring us in the face. 2 raised to what power is 4? N equals 2. So we found that A is second order. Now we've got to repeat for B. For B, I've already identified the two cases where B is different but A is the same are trials 3 and 1. Here it won't matter which one goes on the top ultimately because they have the same order. But if I put trial 3 over trial 1, again I've got the larger concentration this time in the numerator rather than the larger rate. So this would be 8.5 times 10 to the minus 5 equals K times 0.5. I can actually put squared in there now because I know it's second order for A times 0.5, or sorry, B is 1 in this case to the M divided by 8.5 times 10 to the minus 5 equals K, 0.5 squared times 0.5 to the M. Again, these k's drop out. This time the a values, the 0.5 squared drops out. What do I get? 1 equals 2. All right, so I'm not sure exactly where the camera stopped off. This is more for folks in the, watching the video. What we've done is compared trials 3 to 1. We wrote the rate law using one of the lines from our data over here. Obviously some things canceled out. And we got this real simple question, right? 2 raised to what power equals 1? It can only be the 0th power. So B is 0 order. So now we've found N and M. We still have to go back by substitution and find K. Well, it does not matter which trial we use. So let's try trial 1. 8.5 times 10 to the negative 5 equals K times 0.5 squared times 0.5 to the 0th power. So K is going to equal 3.4 times 10 to the negative 4. Now K needs some units. The overall order is going to be second order. So K's units, once again, align with the units of the overall reaction, the second order reaction, so the 1 over molar seconds. And now we can say that the speed of this reaction will always be 3.4 times 10 to the minus 4 molar per, 1 over molar seconds times the concentration of A squared. I don't even need to write the B because it's raised to the 0th power. All right, and that's kind of confusing to some people. You know, how is B part of this process? But once we study what's called the collision theory, it'll become a little more clear. Okay, so really, if you want to control the speed of this reaction, you want to do it through the A. Just dumping in a bunch of B, it's going to do you no good. It's not going to make it go faster or slower. And that's where understanding the kinetics really helps you out when you want to speed up or slow down a reaction. You need to know which chemicals dictate that speed that you're observing. All right. All right. So now we're ready to move on with what ends up being one of the biggest topics in this chapter, and that is what we get to what are called the integrated rate laws. The integrated rate laws are a series of equations that relate concentration of reactants to time. Our other forms of rate expression or rate law that we have so far, one has this form, okay, that we just worked with, and the other one that we started with has this form. This is our average, this is our instantaneous one over here, okay? This one on the left has time in it, but it's kind of got this average block of time, right? This one over here on the right is instant. How fast your reaction is at any given moment. You just don't know what moment it is. You don't know how much time you're talking about. There's no time factor in there at all. So what we need to do is combine these two. We need to get rid of the rate and solve these equations. To do so, we need calculus. And so we're not going to necessarily do the calculus here, but calculus has been used to solve this expression. So depending on what math class you're in right now, maybe you've started to do integration. All right? I think we do that in Calc 2 here. Calc 1 is mostly differentiation, okay? So if you're in Calc 2 this semester, maybe you've started to do some integrals and solve them. And that's what you would need in order to solve this. If I could briefly show it to you, for one of these orders, what you would do is take this negative delta x over delta t equals k x to the n. So this would become, as delta t goes to 0, right? That's what calculus is. You'd make that delta get smaller and smaller and smaller, right? This expression over here becomes negative dx dt equals k x to the n. So you would want to solve this for negative dx x to the n equals k dt. So here's, or in other words, this is x to the negative n dx equals negative k dt. So if you're in a Calc 2 class, I encourage you to start to solve this now, all right, to do the integration. It's a great exercise. It links what you're learning in a different area of your curriculum to what we do in chemistry. Or is that blowing your mind, Morgan?
Yeah.
Why is that?
I don't know.
Are you in Calc 2 or not?
Yeah.
Okay, so have you started to do integrals like this?
Yeah.
Okay, so we are going to use the results of this for the 3 different values of n that we've been looking at so far in this chapter. We could do it for any value of n. Okay, what we do? We'd slap some integrals on here, and that's what we get. All right. So depending on what n is, when n is 0, the solution of this is that x, the concentration at time t, because I'm going to integrate my time from 0 to t, whatever time I'm interested in, just generic placeholder. So the concentration at time t would equal the concentration at 0 minus k times the time t. Okay? When n is equal to 1, the form is going to be the ln of the concentration at time t equals the ln of the initial concentration minus kt. Because you're going to have an x to the negative 1, so the integral of a 1 over x is going to have a logarithm in there, or a natural exponent. Okay? When n is equal to 2, I'm going to get 1 over the concentration at time t equals 1 over the initial concentration plus kt. So these 3 are what we call the integrated rate laws, because they have been solved for or developed through integration down here. Okay, again, if you're not in Calc 2 yet, I'm sorry that this is a little bit ahead. We're not actually doing the calculus. I mean, this is how the calculus would get set up, but this is just the result of it. Okay, but if you're there, I think it's making it. I'm hoping it was a good connection for you, Morgan, that you had. All right, it's not a oh my gosh, a scary connection. It's a great connection to see how one thing helps the other. Okay, now what we often do, because we understand that we're looking for this equation that relates concentration to time, we often don't write this little subscript t here, and it's just implied that this is the concentration at the time t that we're interested in. Okay? Other questions? There were other folks kind of whispering or anything. If you have a question, it might be a question that somebody else has later on, and they wouldn't get a chance to actually ask me. So ask it if you have it. No? Okay. At this point, you just need them. Okay? You don't have to derive them any further. They're on your equation sheets. Okay? We just need them, and we're going to start to use them and see how we use them in chemistry. All right? Now, on the one hand, they're pretty simple to use. Let's just go through a couple of quick examples. Yes?
Are there higher order formulas of that, or is it?
Yes. Every order would have its own unique integrated rate law. So higher orders, you would start to see 1 over x squared. It's just going to become a pattern, actually. If you look at the power of the concentration, it was first power, then the ln, then it's the -1. I think it becomes -2, -3. This just comes out of the integrals that we would have for the higher orders. Okay? So, all right. Let me set up a couple of examples. for how we might use these integrated rate laws. Okay. I'm just going to use a generic reaction. Let's say x to y plus z is a second order reaction with k equal to 0.025 molar per second. Okay. If you begin the reaction with 1.2 molar x, how much remains after 1.0 minutes? I think I need to change my rate constant. I'm going to add another 0. 0.0025. Okay. This is a pretty logical question, right? You're going to start a reaction with a certain amount. How much are you going to have left 1 minute later, 2 minutes later, an hour later? All right? Sort of the flip of this question would be, how long is it going to take to use up all of the reactants, right? When's the reaction going to be done? When do I get to leave lab, in other words? Right? These are the types of questions that these integrated rate laws can answer for us that our earlier versions could not. All right? They could not tell us these connections between how much stuff we have and how much time has passed during the reaction. Okay? All right, so what's key to this is that it's a second order reaction and we're given the K. For a second order reaction, we can write that 1 over x equals 1 over x0 plus kt. And we're after the x. So we got 1 over the initial amount of 1.2 molar plus 0.0025. This is, I gave the wrong units. I keep doing that. 1 over molar and seconds. And then the time is 1 minute. So I do have to convert that to 60 seconds so that the units cancel out. That's a sneaky little thing that often pops up in our kinetics questions because the rate constants will have per seconds, but you might have a time that's, more like minutes or hours. So you have to justify, those two. Okay? All right, so my calculator, 1.2 raised to the negative 1, or 1 over that power, plus 0.0025 times 60. 0.9833. But that's not my answer. That's 1 over my answer, actually. And it's got units of 1 over molarity, which prove that. So I have to, raise it to the negative 1 power, or flip both sides. And I get 1.02 molar as the amount that is left. Okay? Now you get some idea of what your answer should be when you're doing kinetics problems. Because the reactant concentration never increases. It always goes down. So if you're asked a question like this, it's always going to be less than what you started with and greater than what? What's the minimum amount it could ever be? 0, right? So you got to get a number between 0 and your starting value when you're asked about a concentration. If we flip this around and do a time problem, we'll do that in a second. You've got to get a time that's positive. You can't get negative time, right? All right. So you start to think about what are the reasonable windows for an answer, right? And it helps you have some confidence in your answer. Okay. So let's do a different question. How long will this reaction take to use up 70% of the initial amount of x? Okay. How long is it going to take to use 70% of the amount of x you start with? Now the key to solving this problem is to thinking very, very carefully and to understanding the rules of kinetics. The integrated rate laws, okay? So the integrated rate laws, the IRLs, are always written in terms of how much reactant remains at time t. The question could be asked anyway. Here the question is asked about how much is amount being used. But we have to think and answer the question through how much remains at times t. The question could also ask about the products of this reaction. It doesn't matter. We always have to think in terms of reactants remaining at time t. That's what these equations tell us. And so sometimes it adds on these little extra bits and pieces, some stoichiometry or some converting this percentage used to percentage left, like we're going to have to do right now. Okay? So for this problem, when 70% is used, that means that 30% of the initial amount of x remains. Or in other words, x equals 0.3 of what it initially was. Right? So the value of x is 0.3 times the 1.2, or 0.36. So I'm going to use the exact same rate law that I had before, but now I'm not solving for the x over here. I know it. I'm solving for the time. So 1 over the 0.36, because that's how much I have, equals 1 over the 1.2 plus 0.0025 times the t. So I could take 0.36 to the negative 1 power minus 1.2, 1 over that. So far I've got 1.944 equals my 0.0025 times t. So I just divide by the rate constant, and I get 778 seconds. Maybe that's big enough that we can convert it to minutes, right? It's going to be about 12, 13 minutes or so, it looks like. But just keep in mind that you'll be doing these in mastering chemistry. You just pay attention to what unit it puts in the box, and that tells you how you should be answering. Okay? Any questions on that problem? All right, let me do another one to show you sort of a different way we could put together a bunch of these pieces, different order. How about A to produce 2B? If this reaction has K equals 5.7 times 10 to the minus 4, 1 over seconds, how long will it take to produce 0.20 molar B from an initial concentration of A that was 0.30 molar. So this problem is really going to tie together a bunch of things, because the question's asking us about B, our product. So one connection I see that has to be made is, how does B relate to A? Because I have to solve the kinetics from A. as I just had up here earlier in the blue, right? The rate law is always written in terms of the reactant, A, in this problem, all right? And so we're going to have to figure that out. But we're really after a time here. So we got to do some translations. That's what this problem really is at the start. Before we can do the kinetics, we got to do some translations here. In other words, to make 0.2 molar B, how would we, how would we get this, right? To make this much B? Well, let's use our stoichiometry. 2 molar B is made for every 1 molar of A that's used. Now I know that's a little different. We're used to using the coefficients as moles, but molarity is moles per volume. So they should track directly as long as everything is in the same container. All right? If they're in different volumes, then we're kind of out of luck here. And you have to do an additional step. You have to convert molarity back to moles using the volumes. Then you do this part here. All right? But for now, there's no reason to believe they're not. So what this means is, I did it upside down, by the way. I want to cancel the B, so it's 2 molar B in the denominator, 1 molar A in the numerator. So to make 0.2 molar A, I need to use 0.1 molar A. I think I said that wrong. To make 0.2 molar B, I need to have used up 0.1 molar A. But that's not A at this time that we're interested in. Although, actually, no, it's not, okay? So if we have used, next step here, if we have used 0.10 molar A, then our initial amount, 0.3, minus the amount we've used, is going to be the amount that's left. So if we've used 0.1 molar A, then 0.2 molar A is left at this time. Now we're ready to solve. Okay? All 3 of your kinetics equations that I wrote, integrated rate laws, have 4 connected pieces. Concentration at time t, initial concentration, rate constant, and time. To solve for one, you need the other 3. Right? I was given a rate constant here. I know I'm trying to solve for the time. I was given the initial concentration. So these first 2 bits of work were to find the concentration of the chemical at that time. We don't know what that time is yet. Now I wrote ln. That's implying this is a first order reaction. How did I get that? The units. The units. The units up here told me. Okay? I didn't have to spoon feed it to you and say this is a first order reaction. Again, the units, 1/seconds, belong only to a first order reaction. Okay, you can only have those units when your reaction's first order. So it's like staring you right in the face to pay attention to these things. All right. So now I'm after time again. I want to solve for time. So now we can plug in some numbers. ln of 0.2 equals ln of 0.3 minus 5.7 times 10 to the minus 4 times t. So that's going to be negative 0.4, oops, negative sign on that, negative 0.405 equals the 5.4 times 10 to the minus 4, so now divide by that. And I get 751 seconds.
5.7.
Should be 5.7, typo. And that's going to change this, sorry. So a little bit less, 711 seconds. Yep, I should read what my numbers are, I guess, before I write them in there. Okay. So this one's a little more involved. All right. Any questions on it? And so we could solve a bunch of different types of questions now. Anything that connects time and amount can be solved with these integrated rate laws. What we need to know is the order, so we choose the right equation governing the relationship, okay? And then we need to know 3 of the 4 pieces that are in this puzzle in each of the cases. Right? Now there's a lot of other stuff going on with these integrated rate laws. All right. First, the idea of K. K is a little bit abstract. This idea of a rate constant. There's this general, and it is true that as K gets bigger, the rate of the reaction gets faster. So if you're looking at 2 different rate constants, the higher rate constant would tend to mean a faster reaction. But it's kind of abstract, what is a truly big or truly small. So it's we have this way to translate it into something we might understand a little bit better. And that's called the half-life of a reaction. You've probably heard that term before. So the half-life of a reaction is the time required to consume or use up 1/2 of the initial concentration of reactants. And so then if I told you that a reaction had a rate constant of 0.000726, 1 over molar seconds, you might be like, okay. But then I said, the half-life of that reaction is 13 minutes. Oh, 13 minutes to use up half of the stuff. All right, that's not too long. Could probably do that in lab, right? It's not going to be too bad of a reaction. Versus hearing that a reaction has a half-life of like 7 days, or 1.6 billion years, as is the case for some nuclear decay processes, right? We understand time because it's we live in the world of time. And so this is a very useful translation of the rate constant. But so that's really what it is. Half-life is nothing other than a translation of K to give us a hint as to how long it is. So how the half-life relates to K depends on the order of the reaction. Just like the integrated rate laws did, okay? For a 0-order reaction, the half-life is going to be the initial concentration divided by 2K. What you see here is that as you add more stuff, the half-life gets longer. All right? Okay. Makes a lot of sense for a 0-order reaction. For a 1st-order reaction, the half-life is the ln of 2 divided by K. No dependence on concentration. What's interesting with the first-order reaction is that as you add more stuff, the reaction goes faster. Therefore, the amount of time to complete the reaction really stays the same in essence. Okay. In one of the classes this morning, I mentioned a spending spree, right? So if I double your money, I send you on a spending spree one day, then I double your money the next day, you spend faster, twice as fast, so you're going to burn through your money in essentially the same amount of time. Okay, if you're a 1st-order spender. If you're a 0-order spender, when I double your money, you don't spend any faster. You get to spend it for a longer period of time, though. Right? It's going to last you longer. All right. All right. If you're a 2nd-order spender, though, okay. Uh-oh, look out. As I increase your amount, you actually spend even faster, 4 times faster, okay, if I double your amount. And your half-life actually gets shorter, okay. Now, that's just to use up the first half, and then you kind of reset and it slows down dramatically. So it's not like it takes you less time to spend twice the amount of money. In the end, it will take you more, but that first half-life is going to be shorter. Okay? All right. So these are 3 half-life equations. These are also on your formula sheet. All right? And what these are really doing is giving you the rate constant in disguise. All right, so we've got these 3 different equations here, and what these really do is their real job is to relate the half-life to the rate constant. The subtext here is that when given the half-life, you can find K for the reaction, which you'll then use in the integrated rate law. Okay, so you have to use the K in the integrated rate law like we were doing earlier, but if you're given the half-life, it's just sort of like a detour to getting started. Just like being told the amount that was used versus the amount that's being left, or being asked about the product versus the reactant. So there's just different little twists, and this is another one that gets thrown into there. A hint for you, since I'm feeling generous today, in mastering chemistry, you have a question about nuclear decay. If you are a reader of the textbook and skim through it, you'd find this. But nuclear decay is always a first-order process. It doesn't tell you that when it asks you to solve a problem with nuclear decay, so you need to know the order, but it's first order because those processes are first order. That's another sort of drawback of these half-lives. If I tell you something's half-life is 2 hours, I now am hiding what the order of the reaction is. Versus earlier when I told you the rate constant and the units that connect directly to the order, for half-life, the units are always time, regardless of what the order is. So it kind of is a hiding, a way of hiding what that order is. All right? All right, so that's just another little layer. I'm not going to do any problems with them. They're pretty simple. By the way, these equations are solved for very easily using the integrated rate laws. You would just substitute that x is 1/2 of x0 and solve for t. And you would get these in the 3 different equations, these 3 different relationships that we solve here. So it's not like I invented something crazy or whatever. It's just algebra. Yeah. Okay. All right, now the last big piece of this kinetics puzzle that we want to get to today is really the stage setter for our next lab that we're going to do on Wednesday. All right? If I look at these 3 orders of reactions again, n equals 0, see if I can fit this all into one board, n equals 1, and n equals 2. X equals x0 minus kt. ln of x equals ln of x0 minus kt. 1 over x equals 1 over x0 plus kt. Not sure if you can see it or not, but all of these fit the form y equals mx plus b. They're all written in the same pattern. They're all linearized, in other words. Okay? And this becomes the 3rd way that we can study and determine the order of a chemical reaction by an experiment. Okay? So if you follow a reaction and follow the concentration of your reactants at a bunch of different times, okay, and make a graph of concentration on the y-axis versus time on the x-axis, can you see that your x variable is time, your y variable is your concentration, b is the initial amount. There's a connection between the slope of the graph and the rate constant. Okay? This line, generically, because all lines are y equals mx plus b, but this particular line is x equals negative kt plus x0. But this relationship, here's the unique part. If and only if, an important qualifier, it makes it a two-way street, okay? If and only if a reaction is zero order, will a graph of concentration versus time be linear? And thus, the slope is equal to the negative of the rate constant, or the rate constant is equal to the negative of the slope. Over here in the first order case, it would be a graph of ln of x versus time. That would be linear. Okay? And we could match up these parts. So if and only if a reaction is first order, will a graph of ln of concentration versus time be linear? And when that graph is linear, and then thus, again, k will equal the negative of the slope when I equate the two forms. The generic, every line matches y equals mx plus b to my specific case of ln of x versus t. Lastly, for a second order reaction, 1 over concentration would be plotted versus time. This one would go upwards. And we would write here, if and only if a reaction is second order, will a graph of 1 over concentration versus time be linear, and thus k equals m when you relate the two forms, generic line to the specific variables in play here. Now, how does this help us? Sort of related to the question that we had earlier from James. A reaction's order cannot change, and it can be only one value. Therefore, a reaction can match only one of these three potential possibilities. Now, there are third order and fourth order, but we're limiting ourselves to 0, 1, and 2. So if we don't know what a reaction's order is, a new way that we can find the order and the rate constant is to collect concentration versus time data. We know how much we start with. Then we measure the concentration a minute later, or 10 minutes later, 20 minutes later, 30 minutes later, however often we want to. And we make a graph. If the graph, the straightforward graph of concentration versus time is a straight line, we know the reaction is 0 order. And we just take the slope right off of it when the graphing program adds the slope for us. Okay? The slope is just negative of the rate constant. Bam, we're done. We've got the k in the end. Then we can solve whatever other problems we want with that one. But if that graph is not a straight line, it also rules out 0 order as a possibility because of the and only if part. So what do? We take the ln, natural log of our concentration values, and we make a second graph of those values versus time. Now, if this one comes out to be a straight line, it's because our reaction is first order. Bang, we got the order. The slope tells us the rate constant again. If that still isn't a straight line, We go back to the concentrations and we take 1 over them. Plot those versus time, and hopefully it comes out to be, if none of these come out, then it's not 0, 1, or 2. It's a higher order reaction. But your cases will always be 0, 1, or 2 for this method here. Okay? And we get the rate constant here. So only one of these 3 patterns can exist. So here's where the handout comes in that I've distributed.